Okay, so good morning, good evening, and good afternoon, all of you from all over the time zones. And we want to start on time because the webinar is going to take some time. There are a lot of things that we plan to cover. But before we do that, is my audio clear? Just type yes in the chat box if the audio is clear. And just type yes if my voice is clear. Okay, all right, good. And is my video clear? Just type yes if my video is also clear. Okay, all right, good. So let's get started. And this is quite interesting. This particular webinar is a little bit different than what we have been thinking of SOC designs till now. And there is a reason for that. So if I have to give you a context of the whole webinar, we had some open source tools which was available to us, and what these students, especially Pramit and Sayed, the webinar that happened last time, they basically took up the whole the different tool chains and try to figure out a way on how do you basically make use of both and try to create an SOC out of it. It's a very interesting experiment, by the way, because today, in industry also, we use a lot of what do you say, custom kind of techniques to build analog and SOCs. And this particular technique is going to be very soon adopted by some of the top CAD companies. That is the hope, that is the expectation, and it is going to be very soon used, because the way the software has been designed and the way both the software has been designed, it is going to give you a fast turnaround time for designing chips, and that's what the whole webinar is all about. So let's start. So first of all, this is a pre-webinar on OpenFASoC and ALIGN for chip core generation. So in the previous case, in the previous webinar, we talked about analog. We talked about a mixed signal physical design. Remember last time, I think some of you who had attended the last time talk, we had talked about a mixed signal physical design SOC. In generally, if you talk about a chip, if you talk about any chips in the whole world, it's always mixed signal. There is nothing called as only digital chip or only analog chip. There is always it's always a mixed signal chip, and the reason is that because your power lines, your power sockets, those are 230 volts AC, and they are basically then converted to DC, and then we give all the signals to the IOs, and from the IOs the analog signal, some of the analog signals gets entered through the IOs. For example, clock. Clock is generated from a crystal that enters to the IOs. And internally it gets converted to it gets multiplied by PLL, again an analog block. In the whole world, any chip, if you talk about, and especially for students, if you are experts with if you think of a physical design as a mixed signal physical design rather than only digital physical design, that will give you better scope of jobs or attention that you are trying to get in this particular market. Thanks to Parmit and other interns, they were able to get this thing very early as a part of the internship program that these guys did a few weeks back. It was a 10-week program, and they got the crux of physical design, even though they are students. So this is a very good motivational message for all the students out there all over the country, that even being a student, you can still do a lot of physical design, but a real physical design which is mixed signal in the nature rather than only digital physical design, where you run all the flows and all the scripts. We should be trying to learn and understand and focus mostly on the mixed signal part, because in reality that's the case. Okay, so in the previous case we looked into how Sayed how Sayed basically built a whole analog block using an automated flow. And in this particular thing, we are going to take both the analog and digital and mix it and create an SOC out of it. And this particular SOC is now going to be placed and run automatically by the systems or by the OpenFASoC engines that Parmit is going to explain in few minutes from now. Okay, so that's the whole idea, and that's the whole message that we want to pass to all the participants who have joined. So think of all designs, all chip designs, or all the chips in the whole world as mixed signals. And if that is your starting point, I think the going forward, life becomes very easier for you in interviews and in real case scenarios where you're trying to learn new things. Okay. So a little bit about Pramit Kumar Pal. We met him, I think, in one of the hackathons. He was hackathons or workshops, I don't remember, but he was one of the outstanding participants in that particular program. And he has graduated from Maulana Abdul Kalam Azad University with BTech in Electronics and Telecommunication. His expertise is in open source tools for layout design, analog circuits, and VLSI. And trust me, he just like all of you, he's also a student. He just if you see over here, he has just graduated BTech from one of the universities. So there is a huge scope for BTechs if you take the right path, if you follow the right guidance, and if you follow the right instructions. If you do that, there's a huge scope for all of you to learn learn VLSI and semiconductors in the way he did. But keep in mind of exploring new things and exploring different ways of doing things. That is what is going to help you help everybody survive in the industry. And that's what Parmeet and all my interns in the past have done. And he's driven to advance VLSI technology with innovative solutions and a passion for excellence. You will very soon see the way he has made the whole video, and every detail has been captured so beautifully. You will get to know that the amount of hard work that he has put inside the project and making this video, because you must have learned, you must have read this thing somewhere, that doing labs makes you understand the whole task to about 50%, but once you start teaching your labs to 100 other people, that makes sure that you understand the whole concept 95%. So that's the ratio of understanding when you start teaching others and when you start to impart the knowledge that you have to others. So you basically it's pretty sure that you have understood the concept 95%. Okay, so that's the reason behind all these webinars. So I will just quickly invite Pramit and give a few word of advice to all the to everybody who wants to enter into the OpenFASoC and who wants to learn about this particular chip design for students. So Pramit, can you open up your video as well? Yes, Pramit, over to you.
Hi everyone. Yeah, so I started learning about open source tools during my third year. So right now I would say I have over 1.5 years of experience using open source tools. But the zones are so vast that we need to keep on learning and keep on expanding our horizons. Like 10 weeks before, I didn't know about OpenFASoC before joining the VSD internship. So right now, I think I have much better knowledge about FASoC flow and how to generate the automated layouts, and much more are to be explored, but this is just the start. So I would suggest everyone to kindly be attentive throughout the whole webinar, and I hope you can learn few things from this whole effort. Thank you. That's all I have to say.
All right, good. So everybody just stay on the call, and once you have any doubts, you can just put your doubts in the chat box. Pramit will help you to solve all your doubts, and I will let me start the webinar right now. Okay. Just a minute. Okay, so there you go.
My name is Pramit Kumar Pal.
Is it audible? Was that thing audible to all of you? Just type yes if it was audible.
And I'm a BTech.
Okay, all right.
Electronics and Communication Engineering. And today I'm going to talk about using OpenFASoC and ALIGN to generate a complete core for a chip. Now some background info about OpenFASoC. OpenFASoC is a fully open source autonomous SoC synthesis using customizable cell-based synthesizable analog circuits. Well, it's focused on open source automate analog generation from user specification to GDS2 with fully open source tools. This project is led by a team of researchers at the University of Michigan and is inspired from FASoC, which sits on proprietary tools. This is a multi-university and industry effort, and they are members of the CHIPS Alliance. This is also funded by DARPA IDEA program. The SoC synthesis tool realizes analog circuits including PLLs, power management, ADCs, and sensor interfaces by recasting them as structures composed largely of digital components while maintaining analog performance. They are then used to express as synthesizable verilog blocks composed of digital standard cells augmented with a few auxiliary cells generated with an automatic cell generation tool. By expanding the IPXACT format and the Socrates tool from ARM, we have enabled composition of vast number of digital and analog components into single correct by construction design. Let's talk about our design 1-bit ADC. Here you can see the schematic diagram for that, which is designed using Xschem. Here you can see two stages, the first one being 3-stage ring oscillator and a simple comparator. The analog layouts for ring oscillator and comparator are generated using ALIGN. ALIGN is an automated tool to generate GDS2 file formats from input netlists. Here you can see the input netlist, a sample input netlist on the left, and there is a configuration which is necessary to define the power ports, which is VDD and ground. On the right side you can see the layout for comparator and the ring oscillator. After generating the layouts using ALIGN, we have extracted the netlist or the SPICE netlist using Magic tool. Simulation has also been done using open source tool which is ngSpice. These are some important links and references. Thank you, and let's move on forward to the main part of our webinar, which is using OpenFASoC to generate a code for a chip. Okay, so let's start with the installation. We are checking the Python version, and we have found that we are using Python 3.10.6. Next, we have to ensure that pip is upgraded. Next, we are installing IPython, then Jupyter Notebook. Note here that we need to install pip install notebook only, not Jupyter Notebook. Invoking Jupyter Notebook by using this command. Here you can see that Jupyter Notebook has opened up as a web page in Firefox. Here you can see all the directories present. Let's go to desktop, and we are verifying that IPython 3 kernel is installed. Yeah, it is IPython 3. Now we are running the script to install OpenFASoC using the Jupyter Notebook. Well, this can be installed in a different way, like the official way suggested by the GitHub repository, but during installation in my machine, it was creating some errors during compilation of OpenRoad. So I decided to go with this method, and this has been working perfectly. Also, this was also suggested in the Xschem example that was given in the repository, official repository. So I just used that installation code. You can find this in the Google Colab file that is used in Xschem. We are making an OpenFASoC folder. Then change directory to that folder, cd OpenFASoC. Here we can verify that it is changed correctly. Next we run the predefined commands. Here the speed is increased 4 times so that the installation process can be completed in a short period of time. Well, this is a wholly automated process, so any kind of intervention is not required. So it will automatically be installed, and we will just see in a moment that OpenFASoC is being cloned from the repository itself into the folder. Now the OpenFASoC has been cloned. It's almost done. Let's check the directories. So bin folder, conda environment folder, and OpenFASoC folder has been created automatically. So let's check the OpenFASoC folder. Here you can see all the necessary files that have been present in OpenFASoC directory. Tape outs, what is important in here is the OpenFASoC directory, and that's where all the generators are present. Next, we need to ensure that all the declarations and the environment variables are also correctly declared. So it just consists of some library paths and the OpenFASoC root, and also the Sky130 PDK root, which happens to be in the share/PDK directory after this installation. We will now test the installation by running the sample TempSenseGen example. We just need to know what are the commands present in the make file. So for that we will run make help in the TempSenseGen directory. Well, this needs to be edited. TempSense-gen. We'll see that generators are present. TempSense-gen. The spelling is correct. Yeah, it needs to be edited. There we go. We have the contents of the make file present here. Here you can see that the make Sky130 temp verilog runs the verilog generation only, but we are looking for the full flow. So for that we will run this command Sky130 temp -full. Now let's run the whole flow. Let's again change to this directory and run the make file. Make Sky130 temp. So you can see that the whole flow has started on its own. In just a minute we will get all the final GDS files and we can also view them. Some optimization iterations are going on. So after that, we will see DRC checks and IR checks. I think that's done. Here we go. We have the IR report. Number of voltage sources, all PDN are connected. The fan outs, the power report design area. Place and route is finished. DRC is also finished. Extracting the ext files from the GDS. All this uses magic. We have some warnings for the SLC header or the SLC custom block or macro, SLC macro. I think it's done almost. Extracting the topmost level ext file. Yeah, now we are done. So we have total of 26 warnings and there is some error, and this is due to the libui.so file. I think there is something missing in my TCL script file or TCL script directory, but I think the GDS files has been generated. For now, for our test purposes, we have all the files that we need, and let's verify that everything is working correctly. We have the results, Sky130HD, temp sense. Yeah, here we go. We have the final.gds. Now we'll open this in magic using the command magic dash t Sky130A, then dash d xr. Here we are using the xr due to some improvements in the visibility. Well, I saw that if I just open it using normal magic command, it does not, the NVL and PVL is not quite well differentiated, and also if we open it in XR format, then we'll be able to export the whole GDS as an XVG or the whole layout area as an SVG file. So that will be that actually I found that it was easier for me to document the whole thing so that I could just directly export the SVG file from the GDS view of magic. Here is the generators directory, and let's see the temp sense gen directory. We are seeing the make file now. These are the commands which are exactly run by the make file so that all the things are generated correctly. Here is a clean command which needs to be run. If any errors are present, then the clean will reset it all. Temp sense gen.py. This is important. Here the directory definitions are a must because it just ensures that all the files are present and the correct directories are initialized. These are the aux files or the macro custom macros which are inserted in OpenFASoC Flow. Here we are in this example we were using the Sky130 HD version, but there is also a version for Sky130 HS, but that needs to be defined correctly in all the other TCL files. For now, for our purposes, we will just work with Sky130 HD. Well, these are the temp analog, the verilog files where they are present. It's just that. Config.mk is also an important file where lots of definitions are present regarding the VD area or VDD area, core area, like that. These are all the other files that are present in this directory, and but all these files are not necessary for our purposes, but we will just use maybe 3 to 4 of those files. This is the test.json file in which we are specifying all the parameters that are used. This is the source directory. We have all the top level and GDS level definitions. Here we are also defining the macros which are being inserted in OpenFASoC. That needs to be defined also. So we have the topmost verilog, then all the verilogs, the verilog definitions which are needed for the macros. All the dummy instances verilog, as I said, it will be used. As you can see here, we are having the tempsense instant.v file. Well, this is the top level module for this design. We will see in just a minute how that is being defined, and all the temp analog. Well, temp analog lv.v and hv.v are the various definitions for high voltage and low voltage headers that are present. There is a temp sense header in the GDS block directory, which we'll see in a minute. This is the temp sense of the topmost verilog file. Temp analog LV is being used, HV. Next we have the module definition for the temp analog LV. This is the module that is defined for as I said earlier, the header blocks or the macros, GDS macros. All the care must be taken so that we are giving the same name as it is present in the GDS macros and also in the verilog files of those macros. Next we are checking the GDS directory where we are placing all the blocks. Here we need to have GDS files as well as left files. So we'll get to know how to generate the left files from Magic itself. Now we are just checking what are the GDSs. Here we have header.gds and slc.gds. Here we could see that the GDS file did not have any hierarchy set. So that is an important point, and in later stages we will see how to remove that also. This is the pdn.tcl in which we have global connections defined. Here you can see the VDD, VIN and VSS are present. The analog voltage domains are defined, core and temp analog. Here in this example we have two voltage domains, so VIN and VDD. So for that reason we need two domains, the core and temp analog. This is, as I said earlier, that config.mk file is really important, so that's where these definitions are present. Now these lines define the power delivery networks or the power delivery stripes. We will see in a minute how that is being done. The line with the follow pins defines the PDN stripes which are horizontal, and the one without that, the last line or the third line or line number 54, that gives the definition for the specifications for the vertical stripes. We also have the PDN ring, power delivery network ring, which is defined by the line number 53. So here you can see that all the widths, pitch, offset, everything is defined. So if we face errors after the GTS generations in OpenFASoC, we can alter this so that we don't have DRC errors. Live phase DRC errors sometimes, so I had to change it. Here we have the custom net. This is for the V in or the second voltage domain that is being used in this design. We will see in our design later on how this needs to be defined. Well, if this is confusing, these are all the definitions for domain instance that have been present. Let's go into the flow directory. Designs Taiwan 38 instance. These are all the source files that are being imported after you run the makefile command for the whole flow. So the verilog files are generated first, then all the necessary steps are done one by one. This is the config.mk which is present in the design directory of flow itself. Well, this is the secondary power domain that's defined by the VD1 area. Well, this sets up an area which is later on used by some TCL files so that it can generate a custom domain, or it can set a name for that this secondary power area, secondary power domain. These are the definitions for the GTS and LEF files. Pre-global route.tcl, custom connection. This is the constraint.astc file. For our needs, it's not really important now, but it's just present so that sometimes it throws errors. Here we have the scripts directories where all the TCL files are present. Floorplan.tcl is important. Here you can see the die area, core area, site area, everything is present. So here we will later on see that how to make this domain instance in use in the floorplan.tcl. In the OpenFASoC directory, we have the custom connection for the creating custom connection TCL, and this line sets up so that the custom connections which are being done prior to the global routing is free from DRC errors, or it ensures that there are no DRC errors present. So some rules are set up. These are the custom connections. So we will later on see how in our design, or the async counter design, we will see how we have defined the custom connections for VDD, VIN and VSS itself, so that the connection between the macro power lines and the core power lines are connected. Well, we were facing during our trial and error steps that most of the time the connections were not being made, and we were doing that manually, but that's not the correct way. So this is where the connections are being defined. These are read domain instances. Don't have much importance here. These are all the TCL files which are necessary. These are already pre-present, so if you just clone the repository which we have used for async up-down counter, well, you can find this GitHub repository on the link provided. I'll also provide the link to you separately. Here we have the final.v. These are all automatically generated. These are all the field cells that are present. Reports are present in here. Different kind of reports we need to check. DRC reports, we don't have any error. Route DRC is also empty. Antenna log is also empty. Well, before right there we saw that there was some errors regarding the libgui.so file, so that may be the issue why those reports are empty, but later on we will fix that. Now let's dive into the main things which are needed for making our design, the async up-down counter. For that we have already made the comparator.gds files. This is what it looks like. Well, this was already done using ALIGN, and we will also see later on how to do that and how to ensure that ports appear in the extracted spice files. Here you can see all the ports are correct. As you can see, I'm checking out of Vout is present, input is present, INN is present. So everything is present here, but this is not the case all the time. So sometimes we need to manually alter some label names and relabel something so that it appears. These are the spice files. Let's check if the spice file is running correctly or not. We are using ngspice command. It is working actually correctly, but due to some capacitances or stray capacitances, we are having the non-ideal waveforms. We now need to prepare the GDS files for OpenFASoC. For that, we are placing it in a different directory, and let's go on with the procedure. Let's open the GDS files. With GDS open. Well, now let's select the port macon. Now we need to extract all ex2 spice scale of ex2 spice. Now ex2 spice output is finished. Let's check if all the ports appear. LPDD is there. INP is not there. Here you can see that it's not highlighted anywhere else, only in the sub-circuit definition. Well, INN is present. Out is also not present, so that's quite an issue. The ground is present. So let's fix that. Well, how to fix that? Well, this is an error which I was facing using ALIGN. So let's see. Here we find out where the out level is present. For that we use a find level command, select the area, check in which layer out level is present. So we can see it's present in the metal 1 layer in cell def comparator 0. We select the area, then check what is present. Well, for ease we are switching to wiring tool using the space bar. Let's draw a slightly extended part of metal 1. Here we are making the same level. Well, this will we will see that this will ensure that the ports show up. This was the out. Uncheck the default and make it sticky so that it comes out. Now we remove the port from the previous one, erase the previous level. You can see the out level is done correctly. We find the level INN next. We have found it. We go ahead with the same procedure of removing the port and relabeling it by extending some portion or the small portions of metal 1. As you can see, it's also present in metal 1 layer. So let's go to text, change it to INN, then make it metal 1. We delete the previous port, erase the label, and we are done for INN and out. We check the port macall, we extract all the things, then run ex2 spice. Let's check the new spice file. VDD is present, ground is also present everywhere, INP is still not present, so let's fix that. Well, INN is present, out is also present throughout the sub-circuit. Well, yeah, we have skipped by mistake the INP. Let's go ahead with the same procedure. Finding the label, checking what layer it's present, using the paint tool or the wiring tool to extend a bit of metal one layer, making new label, deleting the old port and erasing the label. Erase label. Now we can see that we are all done. Next we run port make all, extract all, ex to spice. Let's check the new spice file generated. I hope this solves our issue. Ground is present, VDD is present, INP is present, input negative is present, out is present. That's great. We have all the port definitions appearing in the spice file. So now we are done. Well, this is how we ensure that the port definitions appear in the extracted spice. Let's do the same for ring oscillator also. Same procedure we will follow. We expand it. Another thing that I just missed is here we can see where the box is present or the whole layout, the whole GDS layer starts from. We need to ensure that it starts from the origin itself, because after the OpenFASoC flow I saw that if we skip this step, then some of our the GDS macros were not in the current desired position, so they were off by some pixels. Yeah, this is where you see that it's off by minus 0.59 microns. So we are selecting it by pressing A, then we move it to origin. Before that we need to set the grid to 1 micron so that it's easier. Yeah, now we have set it to 0,0 origin. We write this GDS using the GDS write command. Now we are done. We do the port make all command. We read the new GDS, then make the port all command. We see the box. Yeah, we have port make all, left right all. Well, this is how we are using left right all to generate the left files. This is needed for the OpenFASoC flow. Let's check how this appears. Port origin is 0 and all the layer definitions are present, and this seems to be correct. Here we will see the whole flow we have generated. Let's go to GDS comparator. Let's move that to the work week 4 align ring oscillator GDS here. We have it all. Next we have some work to do with the comparator GDS. Now we are ensuring that we have the correct format or correct hierarchy for this design too. We set up the hierarchy using the flatten command. Flatten space comparator. This will ensure that the name is correct, because if we keep the naming convention like comparator underscore 0, that was fetching an issue during the OpenFASoC flow. So we are renaming it to comparator. Load the flattened GDS. Here we will see that everything is of the same color and we don't have any more hierarchy in the design. By selecting the top cell, we have the name comparator. Same procedure, we make the window or the grid size to 1 micron, then move the whole thing to origin. Snap to grid is on. We select the whole area using A, then press M in the desired position. We check using the box command that GDS is moved to origin successfully. Now we can proceed with the other steps. We write the GDS, we make all the ports, then to left write all to generate the left files for this. Now we have set up the necessary GDS and left files that are needed for the flow. We don't need these previous GDS files, we have all what we need. This will go into the blocks directory of our async up down gen folder. We are now defining the verilog file for the comparator block. This is needed. Module comparator, input INN, input INP, output OUT, output out. But here sometimes we were checking that if the VDD and VSS were also needed, but it turns out that's not really necessary. Here we have a really small GDS, so we don't need any more. Next we need the verilog file for the ring oscillator. Module ring oscillator. We have only one output, we don't have any input, so output INP. We have named it as INP so that it makes the whole thing easier. Now we need the whole top module, that's async up down .p. Here we will instantiate the previously defined comparator and ring oscillator verilog files. We have only async up down. Defining the input pins. Input underscore INN. Well, this is the voltage or the custom voltage, user defined voltage, which is being fed to this design. In order to adjust so that we are getting the correct or the as good as possible square wave from the ADC, 1-bit ADC. We have defined everything for this module. Now instantiating the ring oscillator. We have designed it. These are the files which we need to generate. The sync up down, this is the top level file, comparator.v, ring oscillator.v. You can see the input INN, all the files that are present. We check the pins are correctly defined because that can create an issue later on. Let's check our folder directory. Our directory for async up down gen. Here we place the GDS files where we don't need it right now. These are the things which are not needed. These were generated by ALIGN. Here we'll place the new GDS files which we generated before. Here you can see the comparator is done, as well as the ring oscillator. Well, we have generated hierarchical, or the design which is fed into OpenFASoC. These are the left files. Now we'll go for the domain instance. Well, apart from these GDS and the left files, we also need these 5 text files, which includes the up-down domain instances, the VDD connection, VSS connection, and the manual macro placement .tcl. Well, as I said earlier, that custom connections need to be defined so that the automatic connection or automatic routing is being done between the core voltage domain and the macro voltage domain. Well, and manual macro.tcl is needed. Well, this is the async up down domain instance .text. VDD and VSS connections are present over here. Here we can see which pins are depicted for what. The ring oscillator has the voltage, positive voltage as VCC, so we need to write VCC in here. But both of them has ground as GND, so we don't have an issue with that. Next we will see the manual macro.tcl. In the domain instances, we are just defining what instances we have. Well, these are the instances that were defined in the verilog files. If you can remember, the comparator and ring oscillator. This is the manual macro placement, which gives the position or the exact position for placing the macros. If there is any GDS errors afterwards, we will rerun the whole flow by adjusting these macro positions. This is the PDN.tcl. Here we don't have any other voltage domains, so all the other definitions are not really needed. So we have VDD, VSS. We have only one voltage domain, that's the core voltage domain. We are defining the standard cell grid. The horizontal stripes are added with the width and pitch definition. Next we have the ring guard or the power delivery ring. Next we have the vertical stripes. Next we will add the PDN connect. So this ensures that the metal 1 and metal 4. Here you can see that we have used metal 1 in this and metal 4 in the vertical lines and horizontal lines, so that needs to be connected. So for that we have used the add PDN connect. We needed to make the power rings and the power stripes for the connection to be done between the macro GDS and the code domain. Let's see the test.json. We have used a module name async up down, generator name also up down dash gen. We have set up the minimum and maximum frequency. Well, that's really not important, but it was throwing errors before. As I said earlier that we don't need all those Python files, but here as you can see we have just set up the directories correctly, and we have also defined what auxiliary cells are being used. Also we are using the Sky 130 HD platform. These are the verilog files that are being used. We have only 3 verilog files for the design, as the design is really not that complicated. We have the final GDS, final verilog, final STC, and final report. Next we check the parameter.py file. You can see how it's defined: async up down generator, PDB process kit. Here you can see the minimum and maximum frequency which was there in test.json file in the top directory. Let's now go into the make file. We have defined the make file command for the verilog generation, but we are in need of the whole flow, so we have done that. Next we check the flow directory into designs. Design directory. Well, sometimes if we just use the directory name as designs, it throws error. Maybe there is something missing, or some definitions are missing in config files that was creating error before. Then I am sure that everything is correct and only design name is used, design folder name. You can see the manual macro placement to which TCL file is added. Here we are seeing which short circuits, or short circuit meaning which connections are custom connections are needed for connecting the GDS macro and port GDS macro VDD and ground to the port VDD and ground. In the scripts directory, then OpenFASoC, here we have seen the create routable net, VDD and VSS, and we have defined the custom connections. If the VDD custom connection exists, then we are creating a new custom connection variable, environment variable. Next we see the NDR rules. VDD and VSS both are separate. Now we will check some of the TCL files which are important. Yeah, floorplan.tcl is important. Here we don't need all these other things like domain instances, because we are not really using a second domain, so we need to comment that out. Well, it was earlier present in the TimSenseGen example, but here we don't need it, so that throws error and can be commented out. We have the lib folder. Now let's run the whole flow for async up down, because we have more or less defined how the directory structure looks like for the async up down. Well, you can always refer to the repository. We have some errors regarding the permission denied. Okay, yeah, sometimes if we clean the whole thing and there is some kind of error between the lib file that was present in object directory. So if we ensure that we don't delete or we don't clean the objects directory, it runs fine. The whole flow it's just a small design, so it shouldn't take much time. Here we can see we have found 2 macros already. A lot of warnings. We have some violations, but that's been taken care of. We have the SDC file. We have the IR report. All PDN drives are connected. So we have successfully connected the macro voltage domain and core voltage domain. DRC is finished. We have no DRC errors. We are exiting the DRC check and we are running magic in a no console format so that we can generate the ext files and spice files from that. We are done with the flow. Let's check in the flow directory for our results. We have reports. These are all the reports generated. We are really interested in seeing how the result looks like or result GDS looks like. Let's check. Let's open up Magic. Well, you can also open KLayout, but I think Magic is more flexible. Let's open up the GDS, the final.gds. Here you can see that everything is nice and clean. Well, we have one DRC errors. I think that's maybe due to some metal 1 layers. I think. Let's check if the VDD domains are already created or connected to the core domain. Let's select the whole domain. Yes, we have connection between VDD. Here you can see the VDD. These are the ring. This ring is for VDD, and the below one is for VSS. If we tap on these layers using S key continuously, we will see all the layers that are being connected to that specific layer. Here we have the ring out pin, ring oscillator output, analog output. We have the input pin or the input negative voltage pin. This is the custom or user given voltage for the 1-bit ADC. Let's check this pin. We have the output of the ADC. This will give us the digital output, the digital square wave voltage output. Here we have successfully done the whole flow, and we can check that these are the metal 4 layers, which you can see that it is VCC. For the left one is the comparator. Sorry, the left one is the ring oscillator and the right one is the comparator. We have VDD in metal 4 layers, and it is also connected to the power ring, VDD power ring. The VSS also has connection to both the ring oscillator and the comparator as well, which is, you can see here, ground, comparator 0, ground. That's the R-VDD. Well, R-VDD is what we had defined in the custom connections. both the files. That's both for VDD and VSS. Selecting the top cell and flattening the whole GDS so that we don't have any here error. Load the async flat. This is what the final GDS looks like. Selecting the top cell, extracting the design ext files. We have some ones. ex2 spice scale off, then ex2 spice. In this part, we are not really concerned with the extraction of the capacitances, so we have disabled that. Let's see, async flat is here. Input ALIGN, output ADC, ring output RVSS and RVDD. Let's check if the VDD pins are connected everywhere. Well, we have connection. Let's check with the other pins as well. We have the VSS connection. We have the ring out connection. This is the analog output of the ring oscillator. And the digital output, that's the out underscore ADC. We have successfully made the GDS, and we can see that all the ports are correctly showing up in the SPICE netlist. This was due to the previous steps which we did to ensure that in the macro level itself we are having the correct port definitions. You can see these are the filler cells. We now have all the GDS files. It is done. Well, now you can, if you want to document this whole thing, you can export the SVG file right from the Magic. These are all the reports that have been generated, the log files. Let's see the whole log file. We have the IR report. We have the 4 floor plan.log floor plan JSON. We have the power delivery network. We have next, you can check the reports if it's necessary. But for now, we have completed most of the processes and we are almost done.
Okay, so that was it. And if you saw the whole webinar was close to an hour, but to do that, he had to actually spend 10 to 12 weeks on labs. So that's the amount of time that you need to spend to get to this level of perfection. So now we are open to questions. You can unmute and ask any questions if you want to ask, or we can sign off. So anybody has any queries, any questions, anything you want to ask him directly? I have unmuted. You can unmute yourself. You can start videos and ask if you have any questions. By the way, great presentation, Pramit. It was done really very well. Everything was very well explained in detail. And that's the beauty of doing the labs and then doing the recording on your own. Okay, anybody has any queries, any questions? So if there are no questions, it's fine. You can always drop us a question on Slack or WhatsApp or in whichever means you have got access to this particular webinar. That's all we had. And finally, we have to do a photo session where everybody has to turn on their cameras, and we'll do a quick screenshot of this particular webinar. This basically goes as a collage in our internal VST repo. So I would request everybody to turn on the cameras, Pramit, including you, and others also. If you can just turn on your cameras, and we'll do V, and Anaga is going to take a quick picture for all of us. Jayant, Manushankar, Martin, Julian, Ansh, Komal, Par, Sai, Suraj, Shamshad. Okay. All right. Anaga, can you take the quick photo? All right. To this V in front of the camera. V is for victory. And I'll take a quick print screen. In fact, all of you can also take.
I'm not able to put the camera.
Okay, fine. I'll take the pictures. Yeah, no, it's fine. Okay, V and all right, great. So so further, if you have any announcement, anything that I think we are going to launch one workshop in the first week of June. All of you can participate in that particular workshop. And then there are boards. I think if everybody saw the VSD Squadron boards, they are all also available for sale. There will be one more round that will be available. Along with the boards, we got all the lectures of lifetime access to all the lectures. So that is also going to be another announcement. And there are many more. There are many more announcements coming soon. We are also going to do another hackathon very soon in 3 months time frame. So you are also going to hear about that very soon. And yeah, there will be more announcement in the future. All right, thanks everybody. Thanks for joining, and I'll see you all very soon. Thanks, Pramit. Thanks for your time.
Thanks.
Thank you. Bye.